What's up, calculus students? Let's get into lesson 3, which is the product and the quotient rule. It's a fairly simple lesson. The explanation is a little bit harder for why, but it's one of the times where I kind of just say, like, just go with it. What is the lesson? The lesson is when you're adding, finding the slope equation, the derivative equation, is very easy. You could just find the slopes of x cubed, the slopes of sine x. However, when you're multiplying or dividing, things are different. When you're multiplying, we have to use what's called the product rule, which says make sure you have x's times x's. Make sure these have x's. Make sure these have x's. If they're constants, we don't have to worry about this. And we'll talk about that later in the lesson. The slopes are going to be the slopes of the first times the second plus the slopes of the second times the first. There's other ways to write this out that are the same. A lot of people do slopes of the first times the second, or the first times the slope of the second. Like multiplication works in any order. I prefer this way. That's just kind of how I learned, but I see other students do it other ways because of their tutors or because of other teachers. I don't care. Just get the right answer. So let's start with products. We have x's times x's. I use parentheses to denote the product. I see we are multiplying two different functions together, a first times a second, so I use the product rule. I have the slopes of the first times the second, plus the slopes of the second, the slopes of cosine or negative sine, times the first. Now, what's very important, this x and this x cubed cannot be combined, just like this x cubed and that x cannot be combined. So keep them separate. We want to plug in pi. So I have 3 pi squared. The cosine of pi is -1. The sine of pi is 0. Again, this is where trigonometry just pops up and you need to be able to deal with it. And if you are still needing to draw your lines, do it. Pi is over here. Here's 0. Here's pi. I go to the left 1. I don't go up or down at all. That's why the cosine of pi is -1 and the sine of pi is 0. And we are going to have some answers that are going to be ugly. Okay, answers that you're not going to feel comfortable leaving. But they are the answers, and you will leave them, and it's okay. There'll be some times when we need to simplify. We need to be prepared to simplify. There will be other times where simplification is just too hard to do, so we don't have to worry about it. All right? So let's do another product rule. I see x times sine x. So x's times x's. I use the product rule. Slopes of the first times the second, plus the slopes of the second. Whoops. Slopes of sine or cosine times the first. You want to put this x in front? Great. Just don't multiply them together. Let's plug in pi over 2. The sine of pi over 2 is 1. Cosine of pi over 2 is 0. So I just have 1. Then we go into quotients. Well, if you have a top over a bottom, and again, x's, we have functions, x's. If you have numbers, there's other things to do that we've seen that we will do. If they were numbers, we don't have to use the quotient rule, though we could use the quotient rule. We have numbers with the product rule. We could use the product rule if we want to, but we don't have to. Recommend not doing it. So we have these, the quotient rule is the following: the slopes of the top times the bottom minus, this is a very key difference. And because of this minus, that's why I like to do the quotient rule the following way. The same as kind of how I did the product rule. I'll do the slopes of the bottom times the top. And then that's divided by just the bottom, not its slopes, but just the bottom squared. Okay. So the slopes of x cubed over 2x minus 3. I have x's divided by x's. Make sure you know you can't simplify these x's. You can't take this x and cancel by this x because we have subtraction down there. Addition and subtraction, simplification's arch enemy. So don't try to simplify unless you have multiplication. Slopes of the top times the bottom minus the slopes of the bottom times the top all over the bottom squared. Now, I ask you to plug in 1. You could plug in 1 into this as it looks like, okay? And that's fine. However, for your test, you won't always be asked to find a slope and a value. Sometimes you're just going to be asked for the slope equation. Now, for a multiple choice question, you have to simplify. Okay, so I'm going to show you how you would simplify this. So this is us practicing simplification. Again, we could find the value of our slope just by plugging in and just working with the numbers, but let's practice simplification. We get 6x cubed. I'm going to distribute the 3x squared. We get 6x cubed minus 9x squared minus the 2x cubed all over. I'm not going to distribute the bottom just because that's actually not simplified. Like if I ask you to simplify this, what would you do? Well, you would factor. We like to have things factored, not spread out with addition. So like don't simplify when you have a product. And now we can see we can combine our x cubes. If I wanted to, I could factor out x squared. And we got that. Now notice if I plug in 1 here, I'm going to get the same value as if I plugged in 1 here. But again, on your test, you won't be able to plug in values. I like plugging in values just so we get an answer and we can check our answer very quickly just by looking at a number. But for your test, they will ask you, what is the slope equation? What is the derivative? I plug in 1, I get 4 minus 9, which is -5, and I get 2 minus 3 squared, which is 1, so that's -5. Now, that was very easy to plug in. If I do it up here, I get 3 times -1 minus 2 over 1, and I get that -5. So, same thing. Obviously, it's the same thing. When you simplify something, you don't change it, you just make it look different. All right, x's divided by x's. I need to use the quotient rule. Slopes of the top times the bottom. Oops. Minus the slopes of the bottom. Be careful. What are the slopes of 1 minus x? The slopes of 1 minus x is -1. The slopes of 1 is 0. The slopes of -x is -1. Slopes of the bottom times the top, all over the bottom squared. Again, I am simplifying. And I get that after simplifying. But if I plugged in 3 here and plugged in 3 here, I'm going to get the same answer. Plugging in 3, 1 minus 3 is -2, squared is 4, so I get a slope of 1/4. All right, I don't give you any examples of like, hey, remember, you don't have to use the quotient rule here. So I'm going to give you an example here. So new problem. Next to g, let's put an h, which is sine x over 5. And it's like, oh, it looks like a quotient. Pay attention to this problem if you're just skimming through. And let's throw also another new problem. 5 times sine x. So a quotient, a product. I'll show you what we could do to get the answers without using the quotient of the product rule. This is x's over x's, so I will use the quotient rule. The slopes of the top times the bottom minus the slopes of the bottom times the top over the bottom squared. Plugging in pi over 4. Cosine of pi over 4 is root 2 over 2. Sine of pi over 4 is root 2 over 2. Oh, that's great. Literally sitting in the one spot where the sun is hitting. Shifting. Okay. Over pi over 4 squared. Okay. Let's try to simplify. Pi root 2 over 8 minus root 2 over 2 over pi squared over 8. Okay. Multiply the top and bottom of this by 4 to get 4 root 2's over 8. Now I have multiply by the reciprocal here. And like, again, this is maybe a little bit unnecessary, but this is just fun practice. Pi root 2's over 8 minus 4 root 2's over 8 times 8 over pi squared. Okay, that's interesting because now, come on, Mr. Pi over 4 squared is not pi squared over 8. Like Mr. It's pi squared over 16. I made a mistake that you guys always make, which is saying 4 squared is 8. Classic. But this is still interesting. Why do I say it's interesting? Because I'm going to combine these two to be pi root 2's minus 4 root 2's, or pi minus 4 root 2's over 8 times 16 over pi squared. This simplifies to be 2. Oh, brutal. And yeah, like even then I don't really love that. You have 2 times pi root 2 minus 4 root 2 over pi squared. That's the answer. You guys are probably like, what? I don't know how to do that. Can't do that. Like, don't stress out. I'm not going to give you something this hard and you would not see something, not necessarily this hard, but this like, where do I end type of simplification. So like something like this on homework, it's fine if you left it like that. Let's not stress too much. I'm literally not going to have you stress out too much. I'm just going to say this is a little too complicated and you won't see something like that on a test or an AP exam. Okay, let's do this one over the right and then I'll do the other new ones. Slopes of the top times the bottom minus the slopes of the bottom, slopes of sine or cosine, times the top, all over the bottom squared. Plugging in pi over 2, I get 1 minus 0. The cosine of pi over 2 is 0. Over 1, I get 1. The slope of this guy at pi over 2 is 1. Now, new questions. What about sine x over 5? Should I use the quotient rule? You could. However, every time you take the slope of 5, the slope of 5 is 0. Okay, so like if you did slopes of the top times the bottom, then minus the slopes of the bottom, you do minus 0. So let me just show you like the slopes of the top times the bottom minus the slopes of the bottom times the top, which means like this part goes away all over the bottom squared. Well, that 5 and that 25 will cancel to be like a 1 over 5. Interesting. So it's like cosine over 5 is my answer for my slopes. Or you don't have to use the quotient rule if you realize that this can be written as 1/5 times the sine of x. Move that 5 out. Make it just like a fraction times a fraction, like sine x over 1 times 1 over 5, 1/5 times sine x. A constant times a function. We tried to really like push this, and you got to be comfortable with this. The slopes are the constant times the slope of the function. So like the constant just stays. The slopes of 1/5 sine x are 1/5 cos x. That is the exact same as what I had, which was 5 cos x over 25. Okay. So don't use the quotient rule unless you see x's divided by x's. What about this guy? Well, you could use the product rule. But if you use the product rule, the slopes of the first are 0. So here's the slopes of the first times the second, plus the slopes of the second times the first, and I get 5 cos x. Cool, because this is just 0. Well, you could also just remember that a constant times a function, numbers, you could just leave the numbers and find the slopes of the function, and you get the same thing. Okay, so like you don't have to use a quotient rule with numbers. You don't have to use the quotient rule with, you don't have to use the product rule with numbers. We'll talk about next class how we would handle 5 over sine x, because that's a little bit trickier, but it's not next class. We'll talk about this in the last class, the chain rule class. Okay. We got this big polynomial. If you want to spend a long time, you could just like distribute this big polynomial and you'd get something really large. It'd take you a long time to distribute that. This is why product rule is great. I don't have to spend the time distributing everything and simplifying and become like having a polynomial that looks, just like x's time plus x's plus x's plus x's. Rather, let's skip that step and just go straight to an equation of the slopes. Okay, what does that look like? The slopes of the first times the second plus the slopes of the second. I'm going to use parentheses because my slopes of the second are this entire thing. So 4x cubed plus 8x minus 3. I almost made a mistake there. Times the first. This is it. Slopes of the first times the second. Slopes of the second times the first. And a lot of students are like, what do I go now? Do I start distributing now? It's like, well, maybe if this is a multiple choice question and you're asked like, what is the slope equation of h, or what is the derivative of h? You would do that. But what are they asking you for the slope at 1? Do you need to simplify to get the slope at 1? No. And I'm not going to go ahead and practice simplifying. Like, I'm not spending that time for this question. The other questions with the quotient rule, it is valuable to simplify. We're going to see in future questions how sometimes simplification is required and like necessary for us to get the right answer. 5 minus 3 is 2, plus 1 is 3. 4 plus 8 is 12, minus 3 is 9. I have 18 plus 9. 18 plus 9 is 27. That's fun. All right, equation of a tangent line. Let's remember the simplest form of an equation of the line that just has one point and a slope. You already know the x value. It's 3 pi over 2. All you need is a y value and an m. So I need my m value and I need my y value. Now, where does the m come from? This comes from the slope equation. Where does the y value come from? The original equation. I should have put like f of x equals. So I'm going to go ahead and find f of 3 pi over 2. Well, that's the cosine of 3 pi over 2 over 3 pi over 2. Well, I know the cosine of 3 pi over 2 is 0. 3 pi over 2 is straight down. This is why we reviewed trigonometry, because you just like have to be able to deal with it, and it's going to show up randomly. So that's a 0. Now I just need the m. How do we find an m? We need the slope equation. Having a slope equation makes finding the change of the original function, finding the slopes of the original function very easy. So I got the slopes of the top times the bottom minus the slopes of the bottom times the top over the bottom squared. Okay. I will have the sine of 3 pi over 2. The sine of 3 pi over 2 is -1, so I'm going to have this minus sign, and I'm going to have a minus -1, and then times 3 pi over 2. Minus the cosine of 3 pi over 2 is 0 over 3 pi over 2 squared. Well, this becomes a big fat plus. I end up with 3 pi over 2 over 3 pi over 2 squared. Now, you can simplify this in a lot of different ways. One way is to cancel a 3 pi over 2 and realize that you have 1 over 3 pi over 2. I bet you a lot of you are going to make mistakes on this. And you get 2 over 3 pi. That's one way to do it. What's another way to simplify this? And again, like, you got lots of tools in your arsenal, hopefully. You could go ahead and square 3 pi over 2, but like 3 pi squared, 3 pi times 3 pi is 9 pi squared. 2 times 2 is 4. You can then write this as 3 pi over 2 times 4 over 9 pi squared. The 4 over 2 cancels to give you a 2 in the top. 3 in the 9 cancels to give you a 3 in the bottom. A pi and a pi cancel to give you a pi left in the bottom. So that's like another way to do it. Probably what I'm doing is the first way, which was just saying 1 3 pi over 2 cancels with 1 3 pi over 2, leaving us with 1 3 pi over 2 on the bottom, which flips to be 2 over 3 pi. That's my slope. This is my slope of f at x. This is my slope of f at 3 pi over 2. Fun. Let's do another one. So I want an equation of a tangent line. I have the x value. I need a y value and an m value. Let's find the y value. Just going to plug in 4. Square root of 4 is 2. 4 squared is 16. 16 minus 12 is 4. I get a half. Here's my y value. Remember, the square root of positive 4 is positive 2. Okay, great. Now, let's find the slope. The slopes of the top. Okay, well, this is your exponent rules practice. Is going to be 1/2 x to the -1/2. That's the slopes of the top times the bottom. Minus the slopes of the bottom are 2x minus 0 times the top. I'll leave it as root x. All over the bottom squared. Okay. Now I know this can be written as 1 over 2 times 1 over root x or 1 over 2 root x. So I have 1 over 2 root 4 times 16 minus 12, which is 4. This is me finding the slope at 4. These are the slopes at x. This is the slope of y at 4. minus 2 times 4 root 4 over 4 squared. Lots of 4s. This is a fourth times 4, which is 1. This is 1 minus 16 over 16. This is negative 15 sixteenths. And you know what? Like, what am I doing here, guys? When we have equations of lines that we find, it's great to see. So let's go back and let's graph cos x over x. See what that looks like. Oh, fun. It's like a wavy rational function there. And I got y equals 2 over 3 pi x minus 3 pi over 2. And right there, that's our tangent line. It's beautiful. This is telling me that this function, cos x over x at x equals 3 pi over 2, is increasing 2 over 3 pi y's per x. Don't forget, slopes equal change. Let's check out root x over x squared minus 12. And I have 2 vertical asymptotes. But our domain is positive x's because I'm not allowed to plug in negative. So we actually have 1 vertical asymptote. So it's nothing really crazy. And I got y minus a half equals negative 15 sixteenths x minus 4. Yeah. That's beautiful. This function at the point 4.5 is decreasing 15 sixteenths of a y per x, almost 1 y per x. Awesome. All right. Now we get to those questions of like, what else can your slope equation do for you? And this is where we like find x locations, or we're going even further, finding equations of lines that are tangent to this and parallel to this. So this is when we set up an equation to solve. Reminder, keyword, parallel. Parallel lines have equal slopes, so we find this slope. This slope is negative 1/9. I'm going to try to figure out, when does this guy have an m that is negative 1/9? Okay, well, let's get the slope equation, set it equal to negative 1/9 to find the x values. Okay, so slopes of the top times the bottom minus slopes of the bottom times the top, all over the bottom squared. Do we have to simplify? Well, like, guess what? We need to solve this equation somehow. How are you going to solve this equation? Well, you better simplify. This is when simplification is so important, is to help you kind of solve equations or to help you plug in values. Like whenever things get made easier by simplification / are necessary, then we're good. Okay, now what do we do here? Now this is where you guys see like a fraction equal to a fraction. You're like, oh, well, you cross multiply. I'm going to tell you a little secret here, guys. Cross multiplication isn't all that it's cracked up to be. And it sometimes is confusing when dealing with fractions. In this class, you will see like very complex fractions, sometimes equal to each other, where cross multiplying actually doesn't help. So I'm going to let you in on a little secret. You can always take the reciprocal of both sides. What does that mean, Mr. Mester? Take the reciprocal. What do you do in the 1 divided? Like flip both sides. You are allowed to flip both sides. Like that's perfect. Now the x's are up. Things are good. You can multiply by -1. And if you multiply both sides by -1, the -1's gone. And now you have x minus 1 squared equals 9. Now there's 2 ways to handle this. You could go ahead and distribute. This is not my preferred way, but you could do it. Move everything on one side, factor to solve. Or I mean, this way actually prevents us from making very large mistakes. Why do I say that? For this reason, you see you have two x values, 4 and -2. The other way is to square root both sides. However, you have to remember when you're square rooting both sides of an equation, your solutions could be positives or negatives. So like, why is distribution sometimes better? It's because we won't miss out on our solutions. X is -2 and X is 4. If we square root and we just say 3, we're going to miss out because that's not right. This could have been a positive or -3, and squaring -3 gives us 9, squaring +3 gives us 9. So like, heads up, if you're going to do this way, don't forget the plus or minus. So you can squirt both sides, but don't forget the plus or minus. Now I can add 1 to -3 to give me -2. I can add 1 to 3 to get me 4. And like, that's how you're going to get your two solutions. This is the way I prefer. I think it's easier. I think it prevents mistakes. I think it takes less time, but I actually think distribution prevents the common mistake of just taking the square root of 9 and saying 3 and not remembering the plus or minus when you're square rooting. So regardless, there's our x values, but those are not the answers. We want the equation of the line or lines. Ooh, geez. Mr. Messner wants y minus y1 equals m times x minus x1. Okay, well, what do we have? We have m. This is the m that we're looking for. This is the m that we have. If we plug in -2 or 4 into our m equation, we're going to get -1/9. We just solved the equation. We did the work. We showed that these two x values produce an m of -1/9. So like, don't feel like you have to take this and plug it back into your slope equation, because if you do, obviously you're going to produce -1/9. Like, it's something that you'll all do once and you'll be like, oh yeah, I knew that. I was going to get that. And that's okay. So we have -1/9 as our slope, but we have two equations. We have one equation with x equals -2. Okay, so I have the m and I have the x. I need a y. And then I have another equation which x equals 4. I have the m, I have the x, but I still need the y. Where do we find y's from? Plug in x's into original equations, we get y's. Plug in x's into slope equations, you get m's. So I'll plug in -2 into this. Let's get -2 over -3, which is 2/3. I can't wait to graph these. I'm going to plug in 4 into this. I get 4/3 when I plug in 4. Again, I'm plugging into the original equation. Y'all need to do this. Now, what are my answers? These are my answers. Let's get a fancy highlighter out. This is one equation of a line. This is another equation of a line. Those are my two equations. Let's see our work. I just have to. It's just like, it's rewarding to me. Even after all these years of teaching this class, I still enjoy looking at a function, looking at a line, just a random line, x plus 9y equals 1. Okay, that's just a random line. I enjoy creating tangent lines that will end up having that same slope, which makes it parallel, but those lines are located perfectly on the original equation that has the tangent slope, creating this tangent line, and boom, this line parallel to this line, but this line is tangent to the original function. And what's important, I mean, this is just a fun problem to do, but what's important is -1/9. Y is decreasing by 1/9 of a y per x at x equals -2. And let's see the other one, y minus 4/3 equals, again, this is just a fun problem to do. Don't forget the m meaning. Y It's changing. It's decreasing by 1/9 of a y per x at x equals 4. We even have the y value, x equals 4 comma 4/3. Boom. Tangent line, parallel to that line. Cool problem, cool visual. Calculus. Okay. Similar. Okay, so we're looking for a slope of 16. So I'm looking for when does this have a slope of 16? I'm going to get the slopes at x's. Here's the slope of f at x. It will be the slopes of the top times the bottom, minus the slopes of the bottom times the top, all over the bottom squared. And I'm going to figure out when does this equal 16? When will the slopes at x values equal 16? We're going to find those x's. I'm going to distribute. Going to get this. Oh, great stuff right here. Why? Why do I say this great stuff? Flip both sides. This is a great example of like flipping both sides. Homework video tonight. Flipping both sides gives you that. This is what we have. Now, we square root that is probably better than if we square and subtract a 16th and try to factor that, because we'll get x plus 1 equals, what's the square root of 1/16? It's going to be 1/4. Since we are using a square root to solve an equation, I get plus or minus a fourth. Okay, now I need to subtract 1 from a fourth. So let's do 1/4 minus 4/4, and I get negative 3/4. And subtract 1 from negative 1/4, I get negative 5/4. So negative 1 plus or minus a fourth. Negative 4/4, negative 3/4, negative 5/4. Okay, great. All right, but I want the equation of the line. Oh, whew. Thanks, guys. Appreciate it. Thanks, Mr. Messner. Thanks, Mr. Messner. Thanks, Mr. Messner. I think Mr. Messner knew that plugging these into there, that would have been annoying, but not crazy. But we're done. Make sure you know what I'm asking you for. Oh, but we're back. We're back. Okay, so it's parallel to this line. What the heck is this line's slope? Subtract, divide by negative 2. Since I'm dividing two things by one thing, I can divide both of them by the negative 2. And I get negative 1 over negative 2x, which is 1/2 x. I get 2 divided by negative 2, which is negative 1. So I have a slope of a half, really. I feel like this might not work out nicely, but let's find out. Okay. When will these slopes equal this? Let's get our slope equation. Slopes of the top times the bottom, minus the slopes of the bottom times the top, all over the bottom squared. When will this produce a slope of a half? Let's simplify the top. I'm going to go ahead and distribute the 1, distribute the negative 1. Make sure I'm not making any mistakes. Actually, this works out nicely. X plus 1 plus negative 1x plus 1 over x plus 1 squared. Look how simplification is going to help us tremendously. This x, this negative x, gone. This 1 plus 1, a 2. Does Mr. Messner say you can do? I mean, you could cross multiply. Just flip both sides. Oh, now I can multiply by 2. Oh, gosh, I wish I had more space. I'll come up here. Multiply both sides by 2. Bam. Feel free to distribute. Move everything onto one side. Factor so that you get everything. All of your answers. There's going to be 2 of them. If you square root, don't forget that when solving equations using a square root, you need a plus or minus. The square root of 4 is 2, but using a square root to solve an equation, we get this plus or minus 2. 1 plus negative 1 plus 2 is 1. Negative 1 minus 2 is negative 3. These are my 2x locations. I want my equations of my line. I have y minus, I don't know. I have a slope. I have x minus 1. Here's when x equals 1. I have y minus, I'm not sure. I do know my slope. You could double check if you wanted to, but why waste your time? You already know that these x's produce this slope. This is the whole purpose of solving the equation. All we need is our y value. Where do y values come from? Y values come from y equals equations, or f of x equals equations. So let's plug in 1, and I get 0. Let's plug in negative 3. I get negative 4 over negative 2. So I'm just going to do this work up here. Negative 3 minus 1 is negative 4. Negative 3 plus 1 is negative 2. So I get 2. And let's see the work. It's calculus. Did you finish? Yeah. Good. Yeah, we're good. Yeah. X minus 1, x plus 1. Great. X minus 2y equals 2 is just a random equation. Oh, give me a break with this same color here. Let's change that. Okay. Now, give me equations that are tangent to this and parallel to this. Just a fun equation. Remember, this half is like how quickly the function is changing at this x value, how quickly the function is changing at this x value. It's telling me how much we're increasing. Y minus 0 equals, I didn't need that, a half x minus 1. Boom. Beautiful. And then we have y minus 2 equals a half x plus 3. Ba-bam. It's just beautiful. It's just gorgeous. So the slope at this point and at this point is a half. I include a point to have an equation of a tangent. It's just a beautiful visual. The slope tells us how quickly this function is changing at this point. So it's increasing a half of a y per x. So it's increasing, but not very quickly. And these 2 lines happen to be parallel to this random third line. Awesome. Oh, man. I'm really putting you guys through. Oh, my. Oh, geez. All right. I got to speed up. X. Slopes to the top times the bottom. Minus slopes to the bottom times the top. All over the bottom squared. When will the instantaneous rate of change, which is the tangent slope, which is the derivative, when will it equal 12? This is just like me trying to trick you here, guys, like making sure you understand those 3 things mean the same thing. Instantaneous rate of change is the slope of the tangent, is the derivative. All right. We got to simplify. I have to simplify. 2x minus 2. Distribute the negative. Use parentheses. Negative 2x minus 1. Thank you. Thank you. Negative 3 over x minus 1 squared equals 12. Flip. Get me. Oh, that's not going to work. It should be negative 12. Yo, might be. This function is decreasing everywhere. Sorry. But it is an example we could show where if you got, we'd say no solutions. We don't worry about imaginary numbers in this class. You know, fortunately or unfortunately, imaginary numbers are beautiful things. Rather, we just don't deal with it. We say it doesn't exist. It's not a real number. So no real solutions here. So if you got here and you got to no solutions, good. If after changing the problem, you then got here, great. I square rooted both sides. I will then add 1, and I'll get 1 minus a half and 1 plus a half. So a half and 3 halves. Those are x values. Next, what about horizontal tangents? What's so special about horizontal tangents? You know what's so special about horizontal tangents. Their slopes are 0. When will the slopes equal 0? Now, what is so special about the number 0? Well, 0 divided by anything is 0. If you end up with a fraction equal to 0, you don't care about the bottom. Now, you got to pay attention to the fact that like x can't equal 16. Like you're not allowed to plug in 16 because it doesn't exist on the original function. Like there's a vertical tangent. So like it's important just to remember like, okay, if I get an answer that is 16, that's not really an answer because there is no function. We are not defined. We have a vertical asymptote at x equals 16. So just like that's a good little reminder. We're not going to get the answer x equals 16. But I have a fraction equal to 0. I don't care about the bottom. I can essentially ignore it and just worry about the top, provided I remember x can't equal 16. So I'm going to distribute. I got 2x squared minus 32x's minus an x squared. When does that equal 0? That's the only part that I care about. And I get x squared minus 32x. That was a nice breeze. And I get x minus 32. I get when x is 0 and when x is 32. Am I asked for the x coordinates? Yeah, like I want to see this. 0 and 32. X squared, x minus 16. I mean, that actually makes sense probably because of symmetry, that if 0 is one place and you have a vertical asymptote at 16, that the other side of 16 would be the other vertical asymptote. Are you? There you are. Okay. Boom. That looks like a horizontal tangent right there. Boom. That looks like a horizontal tangent right there at 32. Cool. Next. Thank you, Mr. Messner, for just asking for x coordinates, not for equations. Less work that I have to do. Horizontal tangents, slope is 0. Very, very important questions, these horizontal tangent questions, because next unit, that's all we're going to be doing is like focusing on horizontal tangent locations. When do derivatives equal 0? Now, I do want to write the slope equation, but I know that like I can plug in any x. This is always going to be positive. This will never equal 0. It's just good to know that like I can have any x value that I want. Now I am having a fraction set equal to 0. What do I care about? I just care about the numerator of the fraction equaling 0. I get 2x squared plus 32 minus 4x squared. Like I'm getting the same answer. No, I'm not getting the same answer. I get negative 2x squared plus 32 equals 0. I'm going to factor out a negative 2. And I know that this factors. This is a good question. Or I know that both positive and negative 4 make this 0. So, and I want to see. I want to see. I want to make sure I did the right thing. I have caught myself making mistakes in the past by checking myself graphically. Thank you, Desmos, for being able to do things easily. Oh, this is a interesting situation. There. Like Desmos even actually points out where we have horizontal tangent locations. Like it does its own little numerical analysis and figures out that's a max, that's a min. I'm gonna put that point down. So that's cool. All right, last three. The horizontal tangents you realize are not as hefty of problems because you only have to worry about the numerator. Slope of the top times the bottom. Slope of the bottom times the top. Bottom squared. Am I going to skip it? Am I going to skip it? I'm going to skip it? I'm not going to skip it. Don't skip it or else you're going to forget. So I'm not going to skip it. Okay. Ooh. Top times the bottom minus slope of the bottom times the top. Almost made a mistake. Okay. Distribute. Now ignore the bottom. Just make sure your solution is not 2. Is it going to be 2? Is it going to be 2? No, it's going to be 2. 0 and 4. I want to see 2x squared, x plus 2, x minus 2. Bam, 0, 4. Oh, bam. All right. Some more where probably simplification is going to be a little bit tougher. So slopes of the top times the bottom minus the slopes of the bottom. Ooh, times the top. Ooh, oosh. Ugh. Oh, whatever. We'll be fine. Remember we're subtracting this. All right. I got 2x squared. I got 2 x's. I got x's. That's 3 x's. You want to box it up? Box it. I got 1 and 1. I don't care about the bottom. I distribute the negative. Don't forget to distribute the negative. I get negative x squared. I get negative 2 x's. I get positive 3. When does that equal 0? I will factor out a negative 1. This is actually important, guys, for our future. Don't divide by negative 1 because you're like, this is equal to 0. Like our entire slope equation, all elements of it matter. Don't let anything disappear on you. Now we're solving this equation, yes, but for future analysis, my advice is factor, don't slide and divide. It might hurt you. Bam. X equals negative 3, x equals 1 are the two x coordinate locations where that function has a horizontal tangent. X plus 1, x squared plus x plus 4. One. Negative 3. Well, bam. Horizontal tangents, horizontal tangents. Yeah, I'm just gonna say. I was gonna say that this one. I remember doing this one last year, 2 years ago, and it's like, oh, this is brutal. It works out, but like, let's not waste our time. Let's make sure we understand the key product rule, quotient rule, simplification when necessary, when asked for, or when necessary. Don't use the product rule or the quotient rule. If you have numbers, it's got to be X's and X's. X's and X's. X's and X's times X's and X's divide. If you have numbers, constant times functions, you don't have to use the product rule. Okay? This is something that everybody goes through and struggles with, and then you figure it out. Fractions equal to 0, we just worry about the top. Cool. And that's it. Hopefully this was less crazy than the last lesson. The last lesson, if you're redoing any homework, you're redoing the 2.2 homework over and over again until you can't get any of those questions wrong. Okay? All right. Fun stuff out there. Peace.